All right, let's dive into one of the most powerful formulas in all of science. It looks pretty simple, doesn't it? But this little equation, PV equals nRT, unlocks the secrets of gases all around us, from the air we breathe to the very stars in the sky. So how can one simple formula do all that? Let's find out. I mean, it sounds kind of crazy, right? How could the same set of rules apply to a car engine, a hot air balloon, and something as massive as a planet's atmosphere? Well, that's the absolute beauty of it. This one equation connects the invisible world of tiny, bouncing particles to the very real world we see and feel every single day. So what's the common thread here? It's this formula. Think about it. It explains the compressed air in a scuba tank, the powerful explosion that pushes a piston in your car, the gentle lift that makes a hot air balloon float, and even the atmospheric pressure that shapes our weather. It all comes back to this one fundamental principle. And here it is in all its glory, the ideal gas law. PVNRT. Each letter tells a piece of the story about the state of a gas. And that R, well, that's a special little constant that ties the whole thing together. Behind these 5 letters is a whole universe of physics and thermodynamics. It's like a secret code for gases, and today, we're going to crack it wide open. Okay, so to really understand the whole equation, we first need to meet the individual players. Each letter represents a core property of a gas, and the real magic is in how they all relate to each other. So let's start with P for pressure. What is it really? Just imagine billions and billions of microscopic gas molecules zipping around like crazy inside a box. Pressure is simply the grand total of all those molecules constantly smacking into the walls of the container. It's pure chaos, but when you zoom out, it creates this steady, measurable force we call pressure. Next up, we have V for volume. Now, this one's pretty straightforward. It's just the amount of space the gas is in. You know, the size of the container. A gas will always expand to fill whatever you put it in. And as you'll see, squishing that volume is one of the quickest ways to see this law in action. And then we have N. This just stands for the amount of gas we're dealing with. In science, we use a unit called moles. Don't let that throw you off. It's just a word for a really, really, really big number of molecules. Think of it this way. N is just how much stuff you have packed into your container. The more gas you have, the more molecules you have, which means, you guessed it, more collisions. Last but not least, T for temperature. Here's the cool part. On a molecular level, temperature is all about motion. The higher the temperature, the faster the gas molecules are moving. But, and this is super important, for this formula to work, we have to use the Kelvin scale. Why? Because Kelvin starts at absolute 0, the point where all molecular motion just stops. You can't have negative motion, right? And using Celsius or Fahrenheit with their negative numbers would completely break the math. In Kelvin, 0 actually means 0 energy. And this quote just nails it. The pressure we feel isn't one big push. It's the statistical average of an unbelievable number of tiny impacts happening every single second. It's science finding a simple, steady pattern in what looks like complete and utter chaos. Okay, you might have noticed a key word in the name of this law, ideal. So what in the world is an ideal gas? Is it some kind of perfect gas that only exists in a lab? Well, kinda. An ideal gas is basically a simplified version of a real gas that makes the math work out perfectly. We basically pretend that the molecules themselves are just tiny little dots with no real size. We also assume they don't attract or push each other away, they just bounce around randomly. Now, of course, no gas in the real world is perfectly ideal, but for most gases under normal conditions, this model works incredibly well. So this beautiful equation didn't just pop into existence. Nope, it's actually the grand finale of centuries of scientific work. Let's take a quick look at how all the pieces of the puzzle came together. You had scientists like Robert Boyle back in the 17th century figuring out that if you squeeze a gas into a smaller volume, its pressure goes up. Then you had Jacques Charles and Joseph Gay-Lussac connecting the dots between volume, pressure, and temperature. Each one found a crucial piece, but it was the physicist Émile Clapeyron who in 1834 had that aha moment and put it all together into the single, unified formula we know and love today. This is the perfect way to visualize it. Think about a bicycle pump. As you push that handle down, you're decreasing the volume, V. You're cramming all those air molecules into a smaller and smaller space. So what happens? They start hitting the walls way more often, and the pressure, P, skyrockets. That's a textbook inverse relationship, and it's described perfectly by our formula. And listen, this isn't just some abstract theory. This stuff is happening all around you. When you heat the air in a hot air balloon, the temperature T goes up. Those air molecules go wild, they push outwards, increasing the volume, V, which makes the air inside less dense than the air outside. And just like that, you're flying. It's the exact same principle in an engine, just happening way, way faster. But here's what's really mind-blowing. This same law scales up, like way up. The very same rules that make a balloon rise also explain the structure of a planet's atmosphere. And the giant swirling clouds of gas floating between stars, yep, them too. It's just a stunning reminder that the laws of physics are truly universal.
But, like any model in science, the ideal gas law has its limits. It's an incredibly useful tool, but there are some extreme situations where reality gets a bit more messy. And, well, the code starts to break down.
So what happens? Well, if you compress a gas to an insanely high pressure, the molecules get so squished together that their own individual size, which we pretended didn't exist, actually starts to matter. And if you get things super, super cold, the molecules move so slowly that the weak little attractions between them, which we also ignored, start to take over. In those cases, our ideal gas isn't so ideal anymore. So to handle these real-world curveballs, scientists came up with an upgrade, like the van der Waals equation you see on the right. See those extra little letters A and B? They're basically correction factors. The B accounts for the volume the molecules themselves take up, and A accounts for the attraction between them. This is exactly how science works. You start with a simple model, and then you refine it to get closer and closer to the messy truth. But even with those limitations, don't get me wrong, the importance of PV equals nRT is just massive. It represents a fundamental truth about how our universe is put together. So what's the secret sauce that holds it all together? It's this guy, R, the universal gas constant. Its value is about 8.31. That number is the magic constant of proportionality that ensures this whole relationship between pressure, volume, amount, and temperature always works. And the universal part? It's the same for any ideal gas. It doesn't matter if it's oxygen on Earth or some exotic gas in a galaxy far, far away. R is the constant that stitches the law together across the entire cosmos. Because it's so powerful and yet so simple, this one equation is an absolutely essential tool. I mean, chemists, physicists, engineers designing jet engines, meteorologists forecasting the weather, scientists exploring space, they all rely on it. It's truly a cornerstone of modern science. And really, that's the big takeaway here. This is one of the most beautiful examples of how science can find a simple, elegant order in a system that looks like nothing but random chaos. It connects the world of the incredibly small to the world of the incredibly large, all with one stunningly simple law. It really makes you wonder, doesn't it? Our universe is filled with all this mind-boggling complexity, but maybe, just maybe, underneath it all, there are more simple, elegant rules just like this one, waiting for us to find them. It's a reminder that we are far from done exploring. What's the next code we're going to crack?